So this is section 3.4, derivatives as rates of change. We've already looked at this a little bit. So what kinds of rates of change do we see in our reality around us? So examples of rates of change are velocity. So when we drive a car, we measure in miles per hour. In physics, often we do meters per second. Acceleration, which is a change in velocity. And so acceleration for driving a car would be miles per hour per hour. So miles per hour, which is often rewritten as miles per hour squared, and squared hours always freak me out, so I like that one. In a physics problem, we would take velocity in meters per second and look at per second change of the velocity. So I like to say meters per second, but most physics people just say, it's meters per second squared. Other examples, population change. So that could be something like people per year, per month, or per day, per some time unit. Or like there's lots of measurement going around with COVID-19 and like new cases per day. So that's like a population change. Part of the population is changing in terms of who's getting COVID-19. And so those rates are looked at constantly, trying to figure out how do we mitigate all of these problems so we can avoid turning away people from a hospital that need urgent care. Other examples, from business applications, we have a change in rate of change of profit and cost and revenue. Use profit, for example, but it could be cost or revenue. And in business, rates of change, they call those margins. So another way to say the rate of change of the profit would be what's the marginal profit. And technically, margin of profit is a per unit thing. And so that's a change in profit per unit change. So that would be change in profit per one additional unit, whatever they're building. So we'll look at some examples of each of these today. Before we do that, I just want to back up a second and take this back to some basic algebra ideas. So just consider y equals 2x plus 1, and a quick graph of that. Straight or vertical, there we go. So if that's 5 there and 3 there, x and y, then this green one, right, we start at 1 and we're used to using slope. Here our slope is 2 or 2 over 1, right? And we go up 2 over 1 and we get a new point. Up 2 over 1 and we get a new point. So here, points were a little messy. My philosophy was if the point doesn't hit the line, just make the point a little bit bigger, and you're sure to hit the line. So we have our rise here, up 2, and our run, right 1. And so when we play with calculus, we're still looking at those ideas, but we're switching over to curves. So you graph a curve relating that idea of slope of a line to a curve. There we go. So let's suppose I have this curve here, and we're zoomed in on it. So I have some initial x value here, and then we go over h. So there's my new x value, x plus h. And then we find the tangent line. Let's put that one red. So this tangent line probably looks something like that-ish, heading out from that point. So when we look at this plus h here, there's where the x plus h hits here, and then there's the actual point on the curve up here. So just a note on a couple of these values here. This over here is my f of x. This is my f of x plus h up there. And then I have my tangent line right there. What does my tangent line look like? Well, that would be y minus f of whatever x value I picked equals the slope, which is f prime of that x value, times x plus h is what I end up with there, that change. So here's my change in x there, here's my change in y there. Right, actually, it's x minus the x value. So x1, x2, like this is y1, and that's y2 there. X minus x plus h is just x, so I get y minus f of x equals f prime of x times h. And if I take this f of x to the other side, I get the slope times the change in x plus whatever y value I started at. So right, let's think about that for a minute here. I start off at this point right here, and let's use blue. And then this says to estimate the next y value, use your slope, and your slope says go up and over so far, and only do that by h, right? So we're scaling the slope by whatever our change in x is, h. And in order to get this next point right there, I had to know where I started at, and I started at y equals f of x. Right, so this is my starting point, kind of like a y-intercept, and then the slope tells me how far to go up and over depending on what h is right there. And this idea right here, that's known as the margin, if we're talking about business. Otherwise, it's just our change in y. And this is going to come up a few times in this course when we're doing different problems. Keep in mind when we find f prime of x, right? Sometimes I call that dy dx. I must number dy. And that comes from the limit as h goes to 0, and sometimes we call h delta x, a change in x. So of our difference quotient, which I'm just going to abbreviate as delta y over delta x there. So our margin is that change. H is some real number like 1 or 0.1 or 0.01. So remember, h or delta x are supposed to be small. Small should be less than 1, but sometimes we let it be 1, especially when we're talking about marginal change. And I'll get to that in an example in a sec. So a couple things are going on here. Why are we bothering doing this? Well, the answer is a lot of times these functions that we're playing with are super complicated, but a straight line is not. So if we can derive from some complicated function a slope function, right? That's what my f of x is. Slope function. in other words, the rate of change, then I can use the rate of change to estimate new y values. And that's super easy. That's just a straight line. Those are trivial to calculate. Provided we have information about the rate of change of the function, no matter how complicated it is, we can simplify it down to a straight line. So that's kind of what this is about right here. And how do we interpret those rates of change? So, page. Let's take, we'll come back to that margin in just a minute. Let's look at a slightly different example, motion on a line. And we've done a couple of examples of like this in the past. Usually distance or displacement is given the letter s over time. And let's suppose we have, how about t cubed minus 4t plus 3 is our displacement function. So this object's moving on a straight line. That describes its position on the straight line at any particular time. And so what we want to know, what's the velocity? What's the speed? And what's the acceleration at any time? The distance between velocity and speed, velocity has a direction. So motion on a line, typically going to the right is positive. Moving in a positive direction, going to the left would be moving in a negative direction. So if this thing's moving left, then that would be negative change. Positive change. So velocity here is just the derivative. So that is v of t is the derivative of position. Pretty easy derivative here. We get 3t squared minus 4. Speed ignores whether it was moving right or left. It's just like, how fast was it going? I don't care which direction. So speed is the absolute value of the velocity. And so for us, that's just the absolute value of 3t squared minus 4. So basically, after we find the velocity, strip the sign if it was negative. Acceleration is just the derivative of velocity. Which is also the second derivative of position. So if we take the derivative of velocity function, 2 times 3 is 6, t to the first, and derivative of negative 4 is 0. So that's our acceleration right there. And let's do a couple of things. I want velocity at t equals 1. I want speed t equals 1, and I want the acceleration at t equals 1. So that would simply just be plug in 1 to the velocity. So here's my velocity. 3 times 1 squared is 1. 3 minus is 3. 3 minus 4 is negative 1. So the velocity is negative 1. And let's suppose we're doing meters in seconds. So meters per second. Speed, then, would be the absolute value of that, which is just 1 meter per second. All right, so the interpretation of these two together is this: at 1 second, this thing would be moving left at 1 meter per second, is the interpretation here. Acceleration at 1 would just be 6 times 1, or 6, and that's meters per second, or meters per second squared. I like it that way. In the book and homework problems, they can write it as meters per second squared, which is okay. Now, what does that mean? Well, the acceleration is positive, so it's accelerating to the right. Right? If it was negative, that would be like pulling it to the left. Like think about gravity. Positive acceleration is moving up away from the Earth. Negative acceleration is moving toward the Earth, pulling toward the Earth. So this acceleration is towards the right because it's positive. Since A is greater than 0. Now, if I take these two pieces of information together, so what do I know here about this thing? I know that the velocity is less than 0, so that means it's moving left. However, the acceleration is greater than 0, so it's kind of being pulled to the right. Together, these things tell me how the speed is changing. And so what I can say is this thing is slowing down. The object on the line was moving left, but it's being pulled to the right. It's slowing down there. And I can show you what that looks like graphically. So I'm gonna demonstrate this in GeoGebra. And there is a homework problem where you're going to interpret speed. So let's bring up a new calculator here and enter my position function. And I'm going to call it S of X equals, I have to use X here to the third minus 4X. And then what do they have? Plus 3, right? Yeah. So we have to use x's instead of t's, otherwise things get confused. Now the derivative, that's my velocity, that's the slope really. So I'm just going to put a v of x in here for my slope function, and that is 3x squared, oops, equal sign, what was it, minus 4, right? All right, so that's the slope function. Now I really don't want to see that right now, it's just kind of messing things up. Turn that off. And then I'm going to make myself, this is the cool thing I like about GeoGebra, I can make a slider. So I'm going to make a point. Let's see, well, let me use t here, maybe, ooh, let's try to draw something. Let's go t equals 1. Oh, good, it made a slider for me. Cool. And then I'm going to plot that point using t. So you'll see what I'm doing in just a sec. S of t. So there's that point. So now the cool thing about that, once I make that slider here, is I can then use the slider to move the point around. But I want to show you the tangent line. So the tangent line would be y equal, no, y minus the y value, S of t equals slope is v. Don't worry about how I'm doing this, but the result is kind of cool. And then x minus whatever t is. All right, so there's my tangent line right there. So as I move my slider, I can see the tangent line change. All right, so what I can see right here, and I can grab the point and make that happen too. So over here, right, at and near 1, the slope is definitely negative. Now watch what's happening though. So would you agree that it is steeper here, that line is steeper there than it is down here? Does that make sense? Over here, steeper, over here, less steep, less steep, less steep, less steep. All of a sudden it's like not steep at all, it's shallow, but then it switches direction. So now the slope is positive. So a way to think about that is like way over here, if we could go back in time, the function is moving left because I have a negative slope there. But then notice that as I move the point, the slope is getting steeper. So it's speeding up in a negative direction. But then we get over around here, and then it starts to get less steep. And so now it's slowing down there. Why is it slowing down? Because the tangent line, the slope of the tangent line is the velocity. And the velocity is changing, right? And we can see that. Let's see, I guess I should graph v of t here too. So v, let's see, m equals v of t. So we can watch those numbers over here on the side panel. So over here, the slope is negative, almost -4. Down here, the slope is more like -3, right? So a slope of -4 is steeper than a slope of -3. So it's traveling faster to the left here than it is here, right? So this thing is slowing down until right over here, wherever that bottom point is, down there, where we're going to get a horizontal tangent line because we switch from negative to positive. And so we're going to spend in a couple other sections in the course analyzing this idea of how the rate of change changes. So over here, we're decreasing at an increasing rate, and now we're decreasing at a decreasing rate. And then over here, the position is increasing, and it's increasing faster and faster and faster. So up here, we're increasing, we say an increasing rate. And we're going to keep playing with that idea until you get used to it. And it takes a little time to get used to. Okay, so we are just about out of time for math today. Let's go back up, see where we're at. So we started section 3.4, and because I took some time today to go over some more problems from 3.3, we're about a third of a day behind schedule, which is no big deal. The homework questions cover 3 kinds of problems in terms of interpreting these rates of change. Velocity and acceleration problems, population change problem, and we've done one of those before. I remember somebody asked a question about one. And then these marginal changes that we're looking at, which is basically just the derivative change. And so I will probably have to go over a couple of these. The homework for this section is pretty short, but I think you're probably going to have a couple of questions that we'll go over tomorrow.